Hi everybody and welcome to a new video in the Deep Learning for Audio with Python series. This time we're going to talk about training a neural network, and specifically we're going to look at the theory behind it. So we'll look at two very important algorithms: backward propagation and gradient descent. Cool. So let's get started with the idea of training a neural network. So the high-level overview. So what do we do when we train a network? Well, we basically tweak all the weights of the connections among different neurons so that we can have predictions that are really good. So how do we do that? Well, we basically feed some training data, so inputs and target values to the network. Then we look at the predictions and we calculate the error between the predictions and the expected outcome. And then we use that information for iteratively adjusting the weights. I know this feels like very high level, so we're gonna now look at how that's done precisely. Cool. So again, from a quite high level overview, there are two main steps here. So when we train a network, we pass a sample, an example input, and that input we use it for doing two things. So we have the input traveling all the way through to the rightmost layer, and we get the prediction there. So we have a forward propagation, forward pass, and then we calculate an error, we use that information, and we backpropagate that error signal, back to the initial layers. So from right to left. Cool. So now let's break down these two big steps, so forward propagation and back propagation, into its sub-steps. So when we have this forward propagation, what we do basically is we get the prediction, and in the end we calculate the error. Then when we have the error traveling back, so the back propagation side, we do two things. We calculate the gradient of the error function with regard to the weights, and we use that information to update the parameters, because the gradient is going to tell us in which direction we should go, in which direction we should tweak the weights in order to improve the predictions. Cool. So now what I'm going to do is I'm going to go one by one through all of these steps and explain them and explain the math behind it. So get prediction. We saw this already. So we have a previous video where I went through how to calculate computation in neural networks. So if you're interested in the specifics of this, just go back to that one and watch that video. Cool. But in a nutshell, we have inputs. These inputs get propagated to the subsequent layers, on the right, and then until they arrive at the last layer where we get a prediction. Cool. So then we have the next step, which is calculating the error. And for calculating the error, we need an error function. The error function is a function of two variables. So the prediction itself and y, which in this case indicates the expected outcome. Cool. So be aware that many people, instead of using the expression error function, use loss function. So you can use them interchangeably. I prefer using error because I feel it's more, it's clearer to understand what we're talking about. Cool. So we've calculated the error. So now we need to go through the next step. But before going to the next step, I wanted to mention that in this example, we are using the quadratic error function, which is given by this nice formula over here. Nice. Okay, so now we can move to the next step, which is calculating the gradient of the error function. So what we want to do is calculate the derivative of e of the error function with regard to w, so all the weights. So, and if you guys remember, W1, W2, these are the weight matrices. And so these are the weights for the connections between different neurons in different layers. Nice. Cool. So, but how do we do that? Well, first we should think of the of a neural network as a very complex function, which is dependent on two variables. So the x's, which are like this input vector here, x, so the inputs, and w, so all the weights. So if you remember, the error function is a function of p and y, so p being the prediction, but the prediction obviously is a function, is the result of the neural network, so we can substitute this f of x, w for p, and by doing so, we find out that the error function is a function of the weights itself. So it makes sense to calculate the gradient of the error function of the weights because depends on the weights. Cool. So having like all of this knowledge, we can move on and just like review all the elements of a neural network. I hope by now you're very familiar with all of these like elements, but if you're not, I'll give you a quick overview. So we have the x's, which are obviously the inputs. Then we have like the activations. A1 is equal to the inputs. W1, we saw this, it's the weights for the first layer. H2 is the net input vector. So it's all the net inputs for layer 2, and then we just repeat A2, W2, H3, and then finally A3 in this case, which is the prediction itself. Nice. We have this information, we know about the error function and its dependencies, and so what we can do is we can calculate the derivative of E with respect to W2, and we can use a very nice rule from calculus, which I'm not going to review here, but it's called the chain rule. And if we use the chain rule, we can come up with this formula, which rewrites the derivative of the error function with regard to W2. So we have three derivatives for coming up with this main derivative here of the error over W2. And now, yeah, this feels like a little bit intimidating, and I know, and as I said, like this is going to be a quite math heavy video, but I'm going to try to make this calculations as clear and as simple as possible so you can follow and understand what's going on. Cool. So let's calculate these three derivatives here. Let's start from the first one, the derivative of E over A3. Let's remember that we are using the quadratic error function here as the error function. And so if we perform the derivative of E with respect to A3, we end up with this result. So it's basically A3 minus Y. So it's the prediction minus the actual expected outcome. Good. So that's the first block. Second block, the derivative of A3 over H3. Now, for the activations in this example, and as like in the examples for the previous video, we are gonna use the sigmoid function. And so the A3, the prediction here, A3, is gonna be the sigmoid function calculated in H3. Cool. So now if we want to calculate the derivative of A3 over H3, we're gonna end up with the first derivative of the sigmoid function calculated in H3. I'm using this sigma symbol here to indicate the sigmoid function. And the derivative of the sigmoid function is given by this formula here. So it's the sigmoid function itself by 1 minus the sigmoid function. And in this case, it's calculated in H3. Nice. So we have the second element. Let's move on to the third element. So it's the derivative of H3 over W2. So H3, you guys should know this by now, it's given by the matrix multiplication of the activation vector by the weight matrix of the second layer. Nice. So this is basically a linear transformation. And so if we do a derivative of H3 over W2, we are going to end up with A2 with the activations. Cool. Now we have all the three elements that we need to rewrite the derivative of E over W2. So now let's rewrite this. Let's fill this up. So first element. So the first derivative here is A3 minus Y. Then the derivative of A3 over H3 is basically the derivative of the sigmoid function calculated in H3. And finally, the last block is equal to A2. Nice! We have our first element to calculate like the gradient. So we have our error function, the derivative of the error function calculated in W2. Now, what should we do next? Well, we should calculate the derivative of the error function with respect to W1. So we are basically moving from the second layer back towards the first layer. So back propagation. We're going back from right to left. Now, the derivative of E with respect to W1 is equal to this other beast here, but it's not too different like from what we've seen like before. We've just like reused the same like expansion rules, rewriting rules using the chain rule from calculus of of the derivative of E calculated with respect to W2. Cool. So we can get these first element here, so the derivative of E with respect to A2, and using the chain rule again, we can rewrite it as this formula down here with these 3 blocks. Now, if we take all of this and we plug in here, we're gonna end up with this beast formula for the derivative of V with regard to W1, which is given by all of these 5 elements. Now, don't be scared. So it's quite easy to calculate, and good news is that we've already calculated these first 2 elements when we calculated the derivative of V with respect to W2. So we should now focus on these 3 blocks, 3 derivatives now here. So let's start calculating the first one of these 3. So the derivative of H3 with respect to A2. So H3, again, is given by the matrix multiplication of A2 and W2. And when we calculate the derivative here of H3 over A2, we end up with only W2, so the weight matrix for layer 2. Now let's move on. Next derivative. So the derivative of A2 calculated over H2. So again, A2 is basically given by the sigmoid function calculated in H2. And so when we do the derivative of A2 over H2, again, we have the first derivative of the sigmoid function, but this time calculated in H2. Good. Now, final element. So the derivative of H2 calculated over W1. So H2 is given by the matrix multiplication of the input vector X with the weight matrix 1. Nice. So the derivative of H2 over W1 is just the input vector X. Cool. We have all the 5 elements to rewrite the derivative of E over W1. So let's rewrite that. First element here, so the derivative of E over A3 can be rewritten as A3 minus Y. Then we have the second element here, so which is the derivative of A3 over H3, and this is the first derivative of the sigmoid function calculated in H3. So the third block is basically just W2. The fourth block is again the first derivative of the sigmoid function calculated in H2. And finally, we have for the fifth block our input vector X. Excellent. So now we have all the elements for our gradient, which are the derivative of E with respect to W2 and the derivative of E with respect to W1. So do you see a pattern emerging here? Yeah, I guess like you can see something. So look at these 2 elements here, A3 minus Y and multiplied by sigma, the first derivative of the sigmoid function calculated in H3. So they are basically the same as the ones we have here. This is great news because it means that for calculating the derivatives of previous layers here, we can reuse some stuff that we've calculated in layers that are more like towards like towards the end of the network. And this is the whole point of like a backpropagation. So for calculating the derivatives of like the error function in previous layers with respect to the weights, we can use elements that we've already calculated. So let's see this like in action again, now that we know like all the pieces of the puzzle. Cool, so we said that the first phase here for doing backprop is to calculate the error. Then once we have the errors, we use those errors to calculate the first derivative of the error with respect to W2, and then we backpropagate that. We use that information to calculate the derivative of the error function with respect to W1. So we're basically moving all the way backwards from right to left. And so this is the whole point of propagating back the error signal. Nice. So now we have an understanding of backpropagation, so you should congratulate yourself, because I feel there are not many people out there, also machine learning practitioners, who really understand like the math behind backpropagation. Now you do. Nice. So let's go back to the higher level perspective. So the training steps. So we've seen the first 3 steps. So we get the predictions, we calculate the error, and then we calculate the gradient of the error function over the weights. Now the last thing that remains to do is to actually update the parameters, to update the weights. So how do we do that? Well, for doing that, we need a very important algorithm that's called gradient descent, that's also used in traditional machine learning. So how does gradient descent work? Well, with gradient descent, we take a step in the opposite direction to the gradient. So the step, or the size of the step, is basically the learning rate, and the learning rate is a parameter that we use and we can tweak when we do training with our neural networks to obtain better results. Okay, but we now have an understanding like of backpropagation and like of gradient descent, but how does gradient descent like really work? So what does it mean to take a step in the opposite direction to the gradient? Cool. For doing that, we need this graph down here. So on the x-axis, we have the weights, and on the y-axis, we have the errors. Nice. And here we have the error function, which is e as a function of w, obviously, and it's this orange curve here. So let's say we start from this position here. So after we've trained like our network, for example, we've passed in like the first sample, we've calculated the gradient, and we know that we are like at this point, like with the errors and with the weights. Cool. So here we need to calculate the gradient, and the gradient is basically this purple line here. And the gradient, what does intuitively, is to give us information, the direction in which the function increases the fastest, right? Cool. So if we know the gradient, what we want to do is go in the opposite direction to the gradient, because we want to go down in the function, because we want to minimize this function. So we want to go down here to this global minimum where the error of our network is minimized. And so we take the gradient and we basically take a step in the opposite direction to the gradient, where we have like the gradient calculated for all the weights in the network. And so we take a step that's given by the learning rate. So we calculate the gradient here, like when we are like at this point 1, and we jump down here to this point. Now we we have like another like sample in like the network, for example, and it does like forward propagation, like backward propagation. And then when we have like the gradient of the weights of the network, again, we just like take a step in the opposite direction and we go down to 3, then to 4, 5, 6, until we reach the global minimum. And so this is the whole point of training. So we want to tweak the weights in such a way that we can get the minimum possible error. And when we have the minimum possible error, it means that we have good predictions, because the predictions are quite similar to the actual outputs, to the correct outputs. Good. So this was like quite intense, but now I hope you have understanding of both backpropagation and gradient descent and how we use them for neural networks. Cool. So what remains to do? So what should we do like next in the next video? So we'll take all of this theoretical knowledge and we're going to turn it into implementation. So we're going to implement backpropagation and gradient descent, and we're going to expand the multilayer perception class that we've already built so that we can train our network from scratch. Good. So this was the video for today. So I hope you enjoyed it, and if that's the case, please subscribe and hit the notification bell. If you have any questions or doubts about like the content of this video, because it was like quite tough, please leave a comment, leave a questions in the comment section below, and I hope I'll see you next time. Cheers.